Assalamu alaikum wa rahmatullahi wa barakatuh. This is the third part of Chapter 12, Electromagnetic Oscillations. At the end of this chapter, we're going to analyze the free-damped electromagnetic oscillations in the series RLC circuit. Before we start, let's remember the main ideas that we took in the last video. We said that in the undamped free electromagnetic oscillations, the differential equation that governs the variation of UC is given by UC double prime plus 1 over LC, UC equals to 0. The general solution is given by U maximum sine or cosine omega 0 t plus phi, where the proper frequency is 1 over 2 pi radical LC. And finally, we said that the period of the energy is given as T0 over 2. We have the knowledge that for a damped oscillation, there would be a resistive force. In electricity, we add a resistor to the circuit, therefore we call it an RLC circuit. We performed an experiment where we connected a capacitor of capacitance C, which has a charge Q, in series with a purely inductive coil of inductance L and a resistor of resistance R. An oscilloscope is used to visualize the variation of the voltage across the capacitor UAB. So the phase is connected to A and the ground to B. The adjacent figure is obtained. What is special about this curve? It starts from maximum voltage, which is expected since it was initially charged, and then the amplitude decreases with time. We intend to make an analytical study that helps us understand this type of oscillations. For this, we have two methods. The first one is by deriving the expression of electromagnetic energy. The first idea that we should agree on is that the total electromagnetic energy is not constant. This means that the addition of WC plus WL is not constant. Actually, the variation of this energy with time represents the lost power by the resistor that we added already to the circuit. Thus, we write it as minus Ri squared. Now, let's make derivative for this expression of energy so that we can write it as minus Ri squared instead of dW by dt equals to Li prime plus C UC times UC prime. Yet we know that I equals to plus dQ by dt since the positive sense is entering the charged armature Q. Then I, which is Q prime, can be written as the derivative of C UC. The result is I equals to C UC prime. Then we can take C UC prime from this expression and write instead UC times I. We divide by I in both sides of this equation. We get minus Ri equals to Li prime plus UC. Then we're going to replace I in this equation by CUC prime, I prime by C UC double prime, and then it becomes as such. Let's write it then as L CUC double prime plus R CUC prime plus UC equals to 0. Then divide by LC. The final result is this second order differential equation that governs the variation of UC. Now we're going to study the second method by applying the law of addition of voltages. The law states that UAB equals to UAD plus UDB. UAB represents UC, the voltage across the capacitor, while UAD represents the voltage across the coil, but it is opposite to the sense, so we should write it as minus LdI by dt. The same for UDB, which is across the resistor and it's opposite to the sense, so we write it as minus Ri. As we have mentioned in the previous method that I is written as plus dQ by dt Q prime, And finally, it can be written as C UC prime. Then I prime is CUC double prime. Let's replace I and I prime by these expressions. Then rearranging the equation and dividing by LC, we get to the same differential equation that governs the variation of UC. This differential equation is of the form UC double prime plus 2 delta UC prime plus omega 0 squared UC equals to 0, where omega 0 is 1 over radical LC and delta is R over 2L. What about the solution of this differential equation? When R over 2L is small compared to 1 over delta LC, the general solution of this differential equation becomes A exponential minus R over 2L T cosine or sine omega t plus phi, where A and phi are constants determined using the initial conditions of UC and I. Note that the oscillations here is called pseudo-periodic of period t equals to 2 pi over omega, which is greater than the proper period t0. T increases with r. Omega is written then as radical 1 over LC minus R over 2L squared. If R is very small, then T is approximately equals to T0. Now, after defining the solution, we can make a graphical study for U, Q, and I. It's clear from the solution that the amplitude is an exponential function. Representing it, we can find that it decreases with time. Besides, it starts from maximum since it was initially charged. What about the variation of Q as a function of time? Q equals to CUC. Where C is a positive constant, then Q and UC are always of the same variation, but they differ with the amplitude. We end with the current. The current is the derivative of Q. This means that there is a phase difference between I and the Q. This figure shows that the absolute value of I increases with time between 0 and T over 4, while the absolute of UC and Q decreases since the capacitor is discharging through the coil. This shows us that I is negative and I flows in the negative direction. Finally, we are going to study the graphs of energy. Having the expression of UC, the electrical energy is written as half C times the expression of UC squared. This shows us that it is positive for any time. And at t equals to 0, UC was maximum. Then the graph is shown as such, where the amplitude is decreasing and the period of this energy is half the period of the oscillation UC. According to the magnetic energy, it is half Li squared and also it is positive. But at t equals to 0, the current was 0. Thus, it is represented as the green curve in the adjacent figure. Finally, the electromagnetic energy, which is the sum of both. It's clear that it's not constant. It decreases with time due to thermal energy released by R. And it's shown in the blue curve in the adjacent figure. Let's solve an application. In the adjacent circuit, a capacitor of capacitance C, initially charged, is connected with a purely inductive coil and a resistor of resistance R. The electric energy and the magnetic energy of the circuit are represented in the adjacent graph. At t equals to 0, UC equals to 2 volts and I equals to 0 ampere, the first question. Knowing that R over 2L less than 1 over radical LC indicate the type of electromagnetic oscillations that is taking place in the RLC circuit. The answer is, in the presence of the resistor in the RLC series circuit, the type of the electromagnetic oscillations is free damped electromagnetic oscillations. Second part. By referring to the graphs of energies, calculate the value of the capacitance C of the capacitor. Let's check this graph and see what value may help us find the capacitance. It is the electric energy. Thus, we read it at T equals to 0 since it's given. The energy stored in the capacitor at T equals to 0 is 4 times 10 exponent minus 6 joules. And we know that UC equals to 2 volts, it's given. Then, after calculating it, we find that C equals to 2 times 10 exponent minus 6 farad or 2 microfarad. Part 3. By referring to the graph of the energies, find the value of the pseudo period T of the electromagnetic oscillations, then deduce the value of the pseudo pulsation omega. From the graph, we can read the period of energy, which is the time taken by one oscillation. Then it is 2.2 milliseconds. Now, the pseudo period then is 2 times the period of energy, and it is 4.4 milliseconds. What about the pulsation then? It is 2 pi over T equals to 2 pi over 4.4 times 10 exponent minus 3. The answer is 1428 radians per second. The fourth part, determine the differential equation that governs the variation of UC equals to UAB across the capacitor during electromagnetic oscillations in the circuit. We start with the law of addition. It is UAB equals to UAD plus UDB. Referring to the positive sense, UAB is written as UC equals to minus LdI by dt minus Ri. I here is plus dq by dt since the sense is entering the positive plate. So I equals to C UC prime and I prime is CUC double prime. Let's replace them in the differential equation. Thus we get UC equals to minus L CUC double prime minus R C UC prime. Dividing by LC and arranging it, it becomes UC double prime plus R over L UC prime plus 1 over LC UC equals to 0. And the differential equation is attained. Now part 5. Given the expression of UC equals to A exponential minus 2R T cosine 1428T minus 0.1 as a solution for the obtained differential equation and A is positive, determine the value of the two constants A and R. We can start with finding A. Now replacing UC equals to 2 and T by 0, the answer is 2 equals to A cosine minus 0.1. A then is 2.01 volts. To find R, let's use the initial value of I, which is 0. I is dq by dt, which is C UC prime. Be aware that the expression of UC is about 2 time functions multiplied by each other. So in order to make derivative, we should write A, the derivative of exponential, times cosine plus A exponential minus 2R multiplied by T times the derivative of cosine. And the answer is as such. Then at T equals to 0, I0 is 0 ampere. Replace T by 0. We can calculate it and find that R equals to 71.64 ohms. This is enough for this video. Please keep in your mind the main areas that we have mentioned during this video and study well. This is the end of part 3. Thank you for watching.